So we have reached the last derivation under the Euler's equation, where we will deal with the fixed hinged columns. So if I draw the schematic diagram of fixed hinged columns, it is going to be something like this. We have a hinged condition here, we have a column here, and you have a fixed condition here, which is taking up a load P axial. So the free body diagram is given over here, where we can see that the axial load P is there on the either side of the support, and at the fixed support you can see a moment here, a reactive moment here. Because of the presence of this particular reactive moment, a reaction will develop at this particular end. So if there is a reaction here, obviously it has to have another reaction here. So there will be one more reaction here. So that's how this R comes into the picture. If you look at the hinged condition, there was no R at the hinged condition because there was no horizontal reaction developing at that position. Here the reaction occurred just because of the presence of M, and now we have an R here. Now the question is, what is the first step we have to follow, which is nothing but the moment about X. So what is that value? It is going to be, you have to consider the moment about P, you have to consider the moment about R, or you have to consider the moment about P, you have to consider the moment about R, and you have to consider the moment about, and you have to consider the moment M also. So these are the reactive moments. So altogether, when you consider the net equation, it is going to be reactive moment mr minus, there will be an r into x, because this is r is located at a distance of x from the point x, and again you have one more reaction, one more moment due to the p into y. So p into y is the moment due to the external load p, and r into x is again going to give anti-clockwise rotation, so that again that takes the negative sign, but mr is a clockwise rotation, so that is going to take the positive sign. Now if we rearrange this equation, or if we equate this equation with ei into d square y by dx square, this is going to be mr minus rx minus p into y. Now what we'll do, we will again shift this p to the left hand side. So this is going to be ei into d square y by dx square plus p into y is equal to minus rx minus m. That's what we are left with. Here, this is not r suffix x, this is r into x. Here you have to understand one thing. As I told you, this mr has developed at this fixed support because it arrests all the moments. Because of the presence of this mr, we have a new force r developed in this location of the hinge, right? That means if we have to balance this mr, there should be an equal and opposite couple, which is created by this r and this r. So if we compare that, we have an r here, which is separated by a length L. We have another r here. It forms an anti-clockwise couple, which is going to balance this mr. Then only the entire system will remain in equilibrium. So using this comparison, or using this idea, we can say that your reactive moment mr is nothing but r into L, the couple. It has to be the same, because as I told you that the reaction, horizontal reaction, has developed at the hinge just because of the presence of this mr, reactive moment. So if you want to compensate, if you want to balance this MR moment, there has to be a couple, thereby another R has going to develop at the other support. These are one at the bottom support and the one at the top support are separated by a distance L. That means equal opposite forces separated by a distance forms a couple, and that couple is going to balance the reactive moment. So we can say that MR is going to be equal to RL, and if we use it over here, we can say that EI into d square y by dx square plus p by y equal to minus r into x minus what? R into L. And if we rearrange this, if we take R outside, I can say that it is going to be L minus X. And if I divide it with EI, then the equation is going to be d square y by dx square plus p by EI into y divided by RL minus X divided by E. Now we have the same situation here. Here we don't have a P here. If we have a P here, we can say that an M is also on the right hand side. Then we can include the coefficient slice along with the M in the solution. So in order to do that, what I will do, I will add a P on the numerator and I will divide with a P. So now, and after that, what I will do, I will keep this P by EI as M and this value of as the A value. So how the solution is going to look like? Y is equal to C1 cos root of P by EI into X plus C2 sin root of P by EI into X plus what? R into L minus X divided by P. So this is how the solution of general solution of the fixed hinged columns going to look like. Now the question is, how will you find the constant values? And the question is, how will you find the values of C1 and C2? To do that, you need the boundary condition. So what is the first boundary condition? Boundary condition 1. What is that? At x is equal to 0, dy by dx is equal to 0. Now, what is the second boundary condition? Boundary condition number 2. At x is equal to 0, we have y equal to 0. And finally, what is the boundary condition 3? We have at x is equal to L, y equal to 0. These are the three boundary conditions we have to use. Now, I'm not going to do in detail about the derivation, because we have already familiarized the procedure that we have to follow. So if we substitute the first boundary condition, that is at x equal to 0, dy by dx has to be equal to 0. And if we after differentiating this equation y and substituting x is equal to 0 and dy by dx is equal to 0, we are going to end up with, this is going to give you the value of C2 as R by P into root of P by E. This is what we are going to end up with. Sorry, there is a small correction, it's not like that. So what we left with is R by P into root of EI by P. This is what we are going to get. R by P into root of P by E. So this is the value of C2. Now we have to find out the value of C1. So to find the value of C1, we are going to substitute the second boundary condition 2, which means at x is equal to 0, y equal to 0, which is going to fetch you the value of C1 equal to minus R into L by P. So kindly substitute it and find out. It's very easy, because if you have any doubt, you kindly refer back to the previous three derivations, then you will understand the procedure. It's very easy. Okay, now we have the value of C1 and C2, right? Now the equation is going to change like y is equal to minus RL by P into cos root of P by EI into x plus R by P into root of EI by P into sine root of P by EI into x plus the last term, which is nothing but R into L minus x divided by P. Now let's apply the third boundary condition, where at x is equal to L, y equal to 0. What we are going to get is 0 equal to minus R L by P into cos root of P by EI into L plus sine plus R by P into root of EI by P into sine root of P by EI into L plus RL minus x divided by P. So if we look here, we can say that, so this has to be 0, right? So what is left with is, if we expand this L minus x, what we are going to get is something like this: tan L into root of P by EI should be equal to L into root of P by EI. That means we are now in a condition like tan theta should be approximately equal to theta, and this happens for a value of theta is equal to 4.4935. Only for this particular angle, tan theta is approximately equal to theta. So if we equate this together, L into root of P by EI equal to 4.4935, and if we square on both sides, we'll get it like L square into P by EI equal to some 20.1915, right? Now this particular value is approximately equal to 2 pi square. You kindly take the calculator and calculate the value of 2 pi square. It's going to somewhat close to 20.1915. Now we can rewrite it like P is equal to 2 pi square EI by L square. So this is the expression for the buckling load for the fixed hinged condition.